Celt 9b is located in the Milky Way galaxy, approximately 650 light-years from Earth, in the direction of the constellation Cygnus. It orbits a star that is significantly hotter than the Sun, and it does so at a distance so small that the planet completes one orbit in just over a day. Measurements show that the day side of Celt 9b reaches temperatures between 4,600 and 5,000 degrees Celsius. For comparison, the Sun's surface temperature is 5,500 degrees Celsius. This means Celt 9b approaches, and in some atmospheric regions rivals, the surface temperature of a star without producing energy of its own. In terms of size, Celt 9b is enormous. Its radius is nearly twice that of Jupiter, and its mass is about 3 times Jupiter's mass. More than 2,000 Earths could fit inside this planet. Over 100,000 moons the size of Earth's moon could fit within its volume. At these temperatures, chemistry collapses. Hydrogen molecules are torn apart into individual atoms. Metals such as iron, titanium, and magnesium exist as gas. The atmosphere itself emits light due to heat alone. Celt 9b is not becoming a star. It is reaching the maximum thermal boundary that a planet can endure before physics itself changes the rules. WASP-33b resides in the Milky Way galaxy roughly 400 light-years away, orbiting a rapidly rotating, high-energy star. The planet's day-side temperature ranges between 3,200 and 3,400 degrees Celsius. This is approximately 60% of the Sun's surface temperature. WASP-33b is about 1.6 times the radius of Jupiter, large enough to contain roughly 1,300 Earths. Tens of thousands of moons could fit inside it. What makes WASP-33b scientifically important is not just its temperature, but the type of radiation it receives. Its host star emits intense ultraviolet energy, which the planet's atmosphere absorbs instead of reflecting. This absorbed energy remains trapped, pushing temperatures higher than distance alone would suggest. WASP-33b demonstrates that stellar radiation type can be just as important as proximity in determining planetary heat. WASP-121b is an ultra-hot gas giant that exists at the edge of what can still be called a planet. Its extreme size and proximity to its star push its atmosphere into a regime normally associated with stellar physics, rather than planetary weather. With temperatures ranging from 2,500 to 3,000 degrees C, the planet's upper atmosphere is so energized that conventional molecular chemistry breaks down. It is located roughly 850 light-years away in the Milky Way. Its radius is approximately 1.8 times that of Jupiter, allowing it to contain nearly 1,800 Earths. At these temperatures, water cannot survive as a molecule. Any water vapor is ripped apart into hydrogen and oxygen atoms, removing one of the most fundamental compounds found in planetary atmospheres. The heat also causes metals such as iron, magnesium, and vanadium to vaporize and rise into the upper atmosphere, where they condense into metal clouds instead of water-based clouds. These clouds absorb and re-emit radiation intensely, contributing to extreme atmospheric heating. The planet's atmosphere is vertically stratified in an unusual way. Instead of cooling with altitude, temperatures increase higher up, creating a thermal inversion similar to what is seen in stars. Radiation from the star is absorbed efficiently by metallic gases, trapping heat and driving the atmosphere towards star-like behavior. In some regions, atoms exist in excited states more typical of stellar envelopes than planetary skies. WASP-121b's atmosphere is also unstable and partially escaping into space due to the immense energy input. This continuous loss further blurs the boundary between planet and star. The planet represents a transition class, a world where gravity still holds a planetary shape, but chemistry, temperature structure, and radiation processes are no longer purely planetary. It shows how, under extreme heat, a planet's atmosphere can begin to function like the outer layers of a star rather than a conventional gaseous world. 5540 Cancri E is an extreme example of how size offers no protection against planetary overheating. Despite being only about twice Earth's radius, it orbits extraordinarily close to its parent star, completing one full orbit in less than 18 hours. This tight orbit exposes the planet to continuous intense radiation that drives surface temperatures to around 2,400 degrees Z's, hot enough to fundamentally alter the behavior of solid matter. At these temperatures, the planet's crust cannot remain solid. Instead, vast regions of the surface are believed to be covered by global lava oceans, where silicate rock exists as a flowing liquid. Traditional geological features, such as mountains or stable continents, are unlikely to survive for long, as molten material would constantly reshape the surface. The planet's brightness varies over time, suggesting active movement of heat and magma rather than a static landscape. Because 55 Cancri E is likely tidally locked, one hemisphere permanently faces its star. On this day side, heat builds continuously, overwhelming any ability to cool efficiently. The night side, by contrast, may be significantly cooler, but heat transfer between the two hemispheres appears limited. This imbalance reinforces extreme conditions rather than smoothing them out. The planet may also possess a thin, unstable atmosphere formed from vaporized rock, but this atmosphere would be short-lived, repeatedly stripped away and replenished by surface evaporation. 55 Cancria illustrates how a failure in heat redistribution can push a small, rocky planet into a permanently molten state, turning it into a world dominated by lava, instability, and thermal extremes. Coro T7b is one of the clearest examples of a planet pushed beyond the physical limits of solid matter. It orbits its star at an extremely close distance, so close that a single year on the planet lasts only about 20 hours. It lies about 490 light-years away, in the Milky Way. It is slightly smaller than 55 Cancri E, with a radius around 1.6 times Earth's, meaning about 4 Earths could fit inside. This proximity subjects the planet to relentless radiation, driving surface temperatures between 2,000 and 2,500 degrees Celsius, hot enough to melt and vaporize rock. Unlike gas giants, Coro T7b is a rocky super-Earth, but its surface does not resemble anything solid or stable. Large regions are likely covered by global magma oceans, where silicate rock exists in a permanently molten state. Under such heat, minerals such as sodium, silicon monoxide, and magnesium do not remain solid. They boil into gas, forming a tenuous, constantly replenished atmosphere made entirely from vaporized rock. This atmosphere is not stable, as the planet rotates and temperatures fluctuate slightly between regions. Mineral vapor can cool, condense, and fall back toward the surface as molten rock rain, only to be reheated and vaporized again. There is no clear boundary between ground and sky. The planet continuously cycles material between liquid and gas phases. On Coro T7b, geology and atmosphere are inseparable. The planet is essentially eroding itself through heat, existing in a state where solid land is temporary and the surface is actively evaporating into space. It represents a world where planetary structure itself is breaking down under extreme stellar force. HD 189733b is a gas giant exoplanet that represents one of the most hostile weather environments ever observed. It orbits extremely close to its parent star, completing a full orbit in just over 2 Earth days. Because of this proximity, one side of the planet is constantly blasted by intense stellar radiation, while the other side remains comparatively cooler, creating a massive temperature imbalance across the atmosphere. This imbalance is the key driver of the planet's most extreme feature: wind. Atmospheric winds on HD 189733b reach speeds of up to 8,700 km/h, over 5,000 mph, many times faster than the strongest hurricanes on Earth. These winds are powerful enough to transport vaporized silicates, which condense into tiny shards of molten glass. The result is sideways, supersonic glass rain, slicing through the atmosphere with immense kinetic force. Although its temperature, ranging from about 1,200 to 2,000 degrees, is lower than that of stars, it is more than sufficient to melt rock and metal. The planet's deep blue appearance, once thought to indicate oceans, is actually caused by light scattering in its thick, turbulent atmosphere, further emphasizing how deceptive and alien it is. HD 189733b demonstrates that planetary danger is not defined by heat alone. The combination of extreme motion, violent atmospheric chemistry, and relentless stellar exposure makes it a world where the weather itself is lethally destructive, an environment utterly incompatible with anything resembling life as we know it.